composition of a compound rather than to use its molar mass, because sometimes you might not know what the whole compound is. So we can use, I guess this kind of goes a few different ways, but we can use the chemical formula in combination with molar masses of its constituent elements to indicate the relative quantities of each element in a compound, which again is extremely useful information. And so this is the mass percent composition, and we'll walk through how to calculate that as well. And a percent, if you don't know, is a part divided by the whole multiplied by 100%. Now, percentages are useful for relaying data and for comparing things, but in terms of calculations, we never use anything as a percent, and it always gets converted back to the proportion, which would be just this part divided by the whole. So what proportion of the whole is it? So the percentage of each element in a compound by mass can be determined from or calculated from the formula of the compound, the experimental mass analysis of the compound, and the percentages may not always total exactly to 100% due to rounding. So we're going to have to use some judgment to determine if we can actually round to a whole number, or if you get fractions of a number, how you convert those into whole numbers, because that can happen as well, especially when we talk about empirical formula. If you have the formula of the compound, we're always going to be assuming that you have 1 mole of that compound. I was hoping to put in some more examples towards this point, but again, got stuck talking to Fraze as much as I like talking to him. So the mass of X, so one of the components of that compound, times 1 mole of whatever that compound would be. So here we're using the molar mass. A lot of the times it's going to be carbon, hydrogen, or oxygen for a lot of these calculations that we're going to do. And then you divide it by the mass of 1 mole of the whole compound. And the reason that we're using 1 mole is that for any molar mass, say for carbon, 12.01 grams divided by 1 mole, right, that's the molar mass of carbon. If we multiply this by 1 mole of carbon, it's going to be 12.01 grams. So choosing 1 mole makes it really easy. That being said, you don't have to use 1 mole for these kinds of calculations because it's a percent. It just depends on how much of the compound there is. So we could assume half a mole of the compound. We could assume 1/4 of the mole of the compound. You could do 0.1 grams. Any mass that you choose, as long as you use that same mass for all of the components, will give you the correct percent mass. It ends out washing out in the end, but 1 mole is the easiest. The experimental mass analysis of the compound, we'll actually talk about a practical way that that's done, but you take the mass of one of the components and divide it by the mass of the whole compound, and then multiply by 100 to get the percent. All right, so what does this look like? For acetic acid, which is the active ingredient in vinegar, calculate the mass percent composition of oxygen in acetic acid. You can see that very little information has to be given for a problem like this. All we know is that we want the percent mass of oxygen for acetic acid. Oh, I should pull this down. And this is where the periodic table is going to become like the conversion table that you use the most. So the first step for this is we need to figure out what the molar mass of acetic acid is, or the molecular mass. So how do we calculate the molecular mass? Yeah, so the way I like to do it is I'll write out all of the unique elements that make up that molecule, and then multiply each of those by the number of those elements in the molecule. So in this case, there's 1 hydrogen written out front, and then there's also 3 more hydrogens that are written farther into the compound. So there's 4 hydrogens. There's 2 carbons, there's 2 oxygens. Does anybody know or remember from Chem 20 why that 1 hydrogen is written in front? Yeah, that's the acidic hydrogen, or the ionizable hydrogen. And then we multiply each of these by the mass. Again, using 2 decimal places because this periodic table has 2 decimal places. Where's my calculator? 60.02? 60.06. Yeah. And again, this is Chem 1, so if you don't need to write those out, you can use the shorthand. And admittedly, I made up this shorthand. So that's 60.06 grams per mole of acetic acid. Okay, so we've got that. Now we want to know the mass percent composition of oxygen in that acetic acid. Yeah, so we need to use the molar mass of all of the oxygen that's in that acetic acid. So that's 2 times 16. So we'll have 32.00 grams per mole of oxygen. And then this is where we're assuming that we have 1 mole of the total compound. So we would technically multiply this by 1 mole and technically multiply this by 1 mole, but those will both give us those same numbers. And then we divide the mass of the oxygen, right? 32 grams of oxygen divided by 2 divided by 6328. So that's the proportion. Multiplying by 100 or moving the decimal place to the right 2 places will give us the percent. Ah, yeah, so this is interesting. So it's 53.28% oxygen. So, right, the answer in a lot of these is up in the top right corner. Why is my answer different than that? Yeah, decimals used for the molar mass, probably different. Yeah, so oxygen would be 15.999, yeah, 4. Nitrogen, I think, is 14.07. Carbon's 12.06 or so. 007. Yeah.
No, 1.009.
Something like that. Right. So again, whatever periodic table you have on the exam, use that. Right. So, right, a lot of these numbers, well, I should say a lot, all of these numbers, aside from the number of atoms in acetic acid, were pulled off of the periodic table. So for a problem like this, you really need to know what these steps are that you need to take to find those numbers. We can also use this as a conversion factor. So mass percent, conversion factor between mass of the element and the mass of the compound. And since percent means per 100, we could rewrite something like the percent mass of chlorine in Freon 112, which is 69.58. If we had 100 grams of the Freon 112, then we would have 69.58 grams of chlorine from that Freon. Freon, by the way, is a ozone-depleting substance. It delivers chlorine atoms to the upper atmosphere, where they catalyze the destruction of ozone. That's why you can't really buy them anymore, for good reason. So any of our percent masses, similar to using 1 mole, when you're trying to use the molar mass to get percent masses, if you have a percentage like this, use 100 grams, because it'll convert straight into, whatever the percentage is in grams over 100 grams of the compound. Still?
It was, his band.
Oh yeah, Freon was used in refrigerators and car air conditioning. So what mass in grams of iron 3 oxide contains 58.7 grams of iron? Iron 3 oxide is 69.94% iron by mass. Where do you start on this problem? Start with what you know, yeah. I mean, great idea. Let's write out everything we know. So we have 58.7 grams of iron. And then we know that iron oxide is 69.94%. Let's say Fe in, what's the formula for iron oxide, iron 3 oxide? I know we haven't covered nomenclature yet. Fe2O3. Yeah, we'll have a whole lab that we spend doing nomenclature stuff. Okay, and what do we want to know for this problem? What is it asking for? Yeah, the mass of iron oxide that would have that much iron in it. I'll write this in here too. That's iron oxide. Okay. Sometimes using percentages, I think it's easy to say, like, okay, if I told you you had 100 grams of iron oxide, how much iron would be in that iron oxide? It would be 69.94 grams. Okay. So we can kind of, and this is the way that I think about these problems, you can use that idea as like, if I knew how much iron oxide I had, and I knew the percentage, which we have, then I could calculate how much iron would be in that iron oxide. That's pretty easy. Multiply the mass by the percentage. Well, not the percentage. Well, you have to convert it into a proportion divided by 100. Right? So we can set that up as basically a formula for this. Right? So if we had, I'll just write in grams of Fe2O3, and if we multiply that by, convert it into a proportion here, 0.6994, then that would give us grams of iron. So if we treat these like variables, and we say that this is X grams of iron oxide and Y grams of iron, yeah, right. So we know what Y is, 58.7. So X grams of iron to oxide, I'll do this in steps, 58.7 grams of iron. So now divide both sides by 0.6994, and that'll tell us how many grams of iron oxide would contain that much iron. That should be 83.9 grams with the correct sig fix. There's actually another way to do this problem. Good question.
Conversion factor.
Yeah. So doing it so that's where There's a different way to do this. If you take your percent mass of iron and you turn this into a conversion factor of 69.94 grams of iron over 100 grams of Fe2O3. And if we're starting with grams of iron, we're starting with grams of iron, we can flip this because those two things are equivalent, and then you can solve for, cancel out the units, right? So that would be the unit analysis way of solving that one. Cool. Any other questions? No? All right, so we kind of touched on this a little bit on Monday when we calculated the number of, I think we calculated the number of molecules of some compound. I said how many atoms of oxygen are in that compound. And that's this idea that we can use the chemical formula of a compound to convert between a certain number of moles of that molecule and a number of atoms, certain number of moles of an individual atom or element in that molecule. Because these subscripts, because the subscripts on these chemical formulas represent a specific ratio. So for C2CL4F2, we could write a conversion from 2 moles of carbon for every 1 mole of C2CL4F2. Or we could write a conversion factor from 4 moles of chlorine per every 1 mole of that molecule. I don't know, there aren't just 2. What would the third one be? There's one more conversion factor we could write. 2 moles of fluorine for every 1 mole C2CL4F2. All right, so those are conversion factors. Chemical formulas as conversion factors. So how do you determine the mass of oxygen in a 7.2 gram sample of aluminum? This one actually solves very similar to the ones we've already done. Yeah, the key thing here is find the mass percent of oxygen in this aluminum sulfate. So aluminum, sulfur, 2 aluminum, 3 sulfur, 12 oxygen. Mass of aluminum is 26.98. Sulfur is 32.06. Oh, it's 0.7 on here. The other periodic table I used, it was 0.6. 16.00. So was the molar mass of aluminum sulfate. So what else do we need to find the percent mass of oxygen? The molar mass of molar mass of all of the oxygen in this compound. Yeah. So we can take this 12 times 16. All right, so 12 oxygens times 16 grams per mole. It's going to be 192. This is a great time to address the fact that these counts of atoms, or like the subscripts for atoms in a chemical formula, those are exact numbers. There's exactly that number of those atoms in every one of those molecules. So when you're talking or thinking about sig figs for something like this, 12 times 16.00 is going to have 4 sig figs. All right, so then the percent mass of oxygen is just the molar mass of all of the oxygen divided by the molar mass of the whole compound. I'm not going to multiply by 100 because it's more useful if we don't. So we can call this the proportion of oxygen will be 0.5. Hard to write units on this because it doesn't really have units. And then we can take this and multiply it by 7.2 grams to get 4.04 grams of oxygen. Is that tracking for everyone? Basically, for any compound, as long as you know what the molar mass is, you can calculate, or actually, sorry, not what the molar mass. If you know what the formula is, you can calculate what the mass percent of any element or combination of elements would be in that compound. Yeah. No, because it's 7.2 grams. Thank you. 2 sig figs. I mean, you passed my test. It was all according to plan. Okay. I am planning also on, again, I wanted to add a slide or two in here at certain points to be like, how fast can we go? Because first time teaching the class, and we haven't really done, I mean, we did the quiz, but I really did good on that. So I just have a hard time judging how fast or slow to go in this class, especially since if you took Chem 20, a lot of this was covered in Chem 20. And so, does anybody want to go faster? Does anybody, actually, I should ask first, does anybody want to go slower? Could have everybody else close their eyes and I'll be the only one looking. It's okay. Move at our own paces. All right. So we can kind of do this process, in a sense, in reverse for empirical formulas. So if we know the mass, right, if we know the formula, we can calculate what percent mass of a compound that's supposed to be. And that's because there's that specific ratio between all of these atoms in a compound. Well, because of that ratio, it goes both ways. If you take a compound and you decompose it into its base elements, you can calculate how many moles of each compound there are. And you can use that to reconstruct at least the simplest ratio between those for that molecule. This is one of the more procedural, the more clear steps to take for any empirical formula problem. More clear steps in this than most other things in chemistry. So if you get those steps, you can kind of just memorize those steps. Right, so like I said, massive elements formed when a compound is decomposed, or if you know the percent composition of a compound, you can calculate an empirical formula. And this is the key restriction of empirical formulas, is that it represents a ratio of atoms, or a ratio of moles of atoms, not a ratio of masses. So we can only calculate this empirical formula from the ratios of moles of atoms, not the masses. Surprised it didn't say here. I'm going to add something to this also. It's the simplest whole number ratio. So for certain compounds, if you decomposed a sample of hydrogen peroxide, and you were able to calculate the mass or measure the mass of all the hydrogen and all the oxygen in hydrogen peroxide. So hydrogen peroxide should be H2O2. The simplest ratio of those two molecules would be 1 and 1, HO. So if you did this decomposition, your math, which we'll talk about how to do the math would come out to 1 oxygen and 1 hydrogen, when in reality, it's going to be 2 of each. And we'll talk about how you can get from the empirical formula to the molecular formula too. So the steps for this, again, very procedural, meaning if you follow these steps, you'll get to the right answer every time. You write down the masses of each element present in a sample of the compound. You convert percentages to grams, again, by assuming 100 grams. And that makes things easy because you just change it from a percentage to grams, and you're done. And then convert the masses to moles using the molar mass for each element. And then, after you've done that and you've calculated the moles of each element, you divide everything by the smallest number of moles. And sometimes two of the elements will have very, very similar numbers of moles. Pick the smaller one, they'll essentially come out to 1 anyway. The only time that this gets tricky is when your results are not within 0.2 of a whole number. So if you end up farther away than 0.2, right? So if you ended up with 1.19, you could probably round that down to 1. Or if it was 1.81, you could probably round that up to 2. This is especially true for lab experiments, where that's the most likely to happen. In terms of problems that you'll get from like ALEX or like homework problems, exam questions, it's going to be closer than that. So if it's not within 0.2, then you're going to take the fractional subscript, and depending on what your fractional subscript is, multiply it by a number to get whole numbers. And you're not just multiplying the one fractional subscript, you're multiplying all of them. We will have an example of that. The basis for why you multiply by these things, to just cover that real quick, is because like 0.2 is 1/5. So if you multiply 1/5 by 5, you get 1. If it's 0.25, right, that's 1/4. This is 1/3. This is 2/5. This is 1/2. Yeah, so each of these things that you're multiplying by is because that fractional subscript can be represented, or at least closely represented, by one of these fractions. This would be 3/4, and this would be 4/5. Sometimes, I mean, if you could remember these, and you can sometimes your calculator, depending on the calculator you have, will convert between fractions and decimals. Might be able to give you an idea here, but that can get a little bit dicey depending on how exact the number is. So if a sample of a compound is decomposed in the laboratory, produces 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen, calculate the empirical formula of the compound. This is going to involve a lot of the same steps. So here we were given just the grams already. Sometimes you'll be given the percent composition. But we can take each of these grams, and I like to do these all in parallel. So 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. And again, remember, the empirical formula is only the ratio of the moles. So we have to convert each of these into moles because those are the actual counts of the atoms in the molecule. And again, those are exact numbers. So debating on how I want to write it out. So this is 1 mole of carbon is 12.01 grams of carbon. 1 mole of hydrogen is 1.01 grams of hydrogen. 1 mole of oxygen is 16.00 grams of oxygen. And so really we end up dividing each of these by their molar mass. And so that's 13.7385. And that's that one. And this one divided by 16. Great, we got the moles of each. So now we want to know the ratio. So how do we find out what the ratio is between these?
You divide by the lowest mole.
Divide by the smallest number of moles. And this is where I said sometimes they'll be really close. So like we have 13.7385 and 13.7625. And smaller of those is 7385. So carbon. So divide everything by 13.7385. And that one's going to be 1. So there's 1 carbon. And then this will divide by 13.7385. And what's that going to be? It was 1.999. All right, I'm just going to write that. And then the last one, 13.7385, is going to be so close to 1. And so like remember here, like what we're getting to is what the actual ratio is between these atoms in this molecule. And they're going to be whole numbers. So like it's safe to take, especially the 1.999, that's going to be 2. So we'll just erase that, and that's going to be 2. All of these were well within 0.2 of a whole number. So then we would take this information and write out our empirical formula as carbon, 2 hydrogens, 1 oxygen.
Some of those mole calculations, would you have done less sig figs? Like for carbon, there's only 165 grams. So would you have done
Oh.
sig figs normally?
Well, okay. So here, like we're in between calculations, so I don't really want to round anything anyway. And you could do these like one at a time, so you never round anything. But yeah, the sig figs are almost inconsequential here. Like they don't really mean anything because we're trying to get to this ratio, which will be a whole number anyway. So yeah, I did just pick sort of an arbitrary number of decimals there. I would, again, like to avoid rounding errors, if you don't round this, or if you round too much, and I didn't even round up on some of these, should have rounded up, or could have rounded up, I should say. Sometimes you'll end up being farther away from whole numbers because you didn't use as many decimals. So I think I tried to use, like at least 5 on each of these?
Yeah, 4 decimal places.
At least 4 decimal places. And that's just kind of to be safe.
Yeah.
Avoid rounding errors. Okay. I'll give you guys some more time and you can work on this one. And the key is to assume 100 grams. So those are the percent masses of each of the compounds.
Finding our alt periodic tables.
This is close. Feel free to work together too. If you get an answer, check with a neighbor. Oh yeah, and there's always calculators if you didn't bring a calculator. Mm-hmm. Yeah.
When I want to multiply that to 2 to get that into a whole number.
Multiply them all by 2.
Yeah, I'll multiply everything.
Yeah. Hmm? Lowest. Divide them all by the lowest. Okay, so hopefully you got at least this far. All right. So, right, they've just divided everything there by the molar mass. That gave us the number of moles of each. And so then we need to divide by the smallest number of moles, easily 0.969375. You can cheat a little bit on that. Okay. And so the first one, 6.5, and then 8.9, and then, well, this is dividing by itself, so that's 1. Cool, so I got 6.5. So how do we deal with that 6.5? Because it's not a whole number and we can't have half an atom. This is not nuclear chemistry. So, yeah, multiply by 2, right? Because 1/2 would be 0.5, but we have to multiply all of these by 2. So multiply everything by 2 and we get 13 carbon. We get 18 hydrogen. And we get 2 oxygens. So then our formula, be C13, H18, O2. I need like, maybe I should start writing all my zeros with like slash through them, so you know when it's a 0 and not oxygen. Cool. Did anybody have any questions trying to work through that one? Get stuck anywhere? All right. So, how do you get the molecular formula? So this is the empirical formula. Remember, empirical formula, simplest whole number ratio. Could be another whole number ratio larger, or whole number multiple larger than this, or for any empirical formula. So because the empirical formula is the smallest ratio, the molecular formula is always going to be a whole number multiple larger than the empirical formula. So you have to multiply it by 2 or 3 or 4 or 5 integers, nothing in between. So molecular formula will be the empirical formula times n, where n is that positive integer. in reverse, it's the molar mass divided by the empirical formula molar mass. So the other way to think about it is that the molar mass will always be the same or larger than your empirical formula. So if you set up, right, trying to solve this problem, trying to figure out what n is, and you divide your numbers and you get a number smaller than 1, then you probably did empirical formula divided by molecular formula. You can just flip those and probably get the correct n, which is that positive integer. So for a compound that has an empirical formula of CH, again, we're going to calculate sort of the masses, or the number of, we're going to calculate the molecular mass of the empirical formula. So we'll have carbon and hydrogen, right? One of each. So multiply by 12.01, multiply by 1.01. That's going to be 13.01 grams per mole. And so we can take our molar mass, which is 78.11 grams per mole, divided by our empirical formula mass. Oh, sorry. 13.02. This is where mental math gets you into trouble. So 78.11 divided by 13.02. Oh, I didn't do anything. 78.11 divided by 13.02. 5.999, which is 6, right? Some random or systematic error. So what do we do with that information? Well, what is the molecular formula then? Or how do we get there?
Is that the integer?
Yeah, this is our whole number, our integer value.
So we multiply it.
Yep. You multiply this whole number integer that we get by the number of each molecule in the empirical formula.
Each atom.
Sorry, yeah, number of each atom. So 6 carbons, 6 hydrogens. Okay. So that's kind of the background for all of how to do it. One way to do this actually in the real world, or the one way that's actually done for compounds that only contain carbon, hydrogen, and oxygen at least, is combustion analysis. So you burn a known mass of a compound inside of a sealed chamber, and then you collect all of the carbon and all of the hydrogen, but you collect them as CO2 and H2O. Because when anything that just has carbon, hydrogen, and oxygen burns, the carbon all forms carbon dioxide, the hydrogens all form water, and then if you know how much carbon was in the original sample and how much hydrogen was in the original sample, then you can use the difference from your original mass to figure out how much oxygen there was. And then using those 3 things, calculate an empirical formula. So one setup might look something like this, where you have your furnace with your sample in it, oxygen's pumped in there, some ignition source, probably electric ignition to start that fire or just heat it up even. And then the gases from that will travel, get caught in the H2O absorber, and then get caught in a CO2 absorber. And so you could probably, for some of these methods, if you knew the exact mass of the H2O absorber before you burn your sample and the glassware and everything, you could use the difference between its initial mass and its final mass to figure out how much water was in there without having to actually go through the process of separating it from the absorber. And same with CO2. And of course, anything that's not absorbed ends up leaving. So a couple sources of potential error there. So let's say we have a compound containing only carbon and hydrogen. Useful to know. It has 1.6 grams of carbon dioxide and 0.819 grams of water. Find the empirical formula of the compound. How do we find how much carbon is in 1.6 grams of carbon dioxide? Yeah, we could use the mass percent. Because if we have the empirical, or if we have the formula, molecular formula for any compound, we can use the molar mass to calculate percent mass, and then use that to find how much carbon is in 1.6 grams of carbon dioxide. So this ends up being a pretty long problem because now we have to calculate the percent mass of carbon and carbon dioxide, and we do the percent mass or hydrogen in water, and then we multiply those by the masses of each. We multiply those by the masses of each, that gives us the mass of carbon and the mass of hydrogen. So for carbon dioxide, I need to start higher. We need the molecular formula first. 2.01, 16.00, and that's 44.01 grams per mole. And then the percent mass carbon will be the mass of carbon that we would have in 1 mole divided by the mass of the carbon dioxide, 1 mole of carbon dioxide. So it's 0.27, and then multiply that by 1.60 grams of carbon dioxide. So there's 0.4366 grams of carbon. And then repeat the process for water. 2 hydrogens, 1 oxygen. So it's going to be 18.02. And then it's 2.02 divided by 18.02. So it's going to be 0.112097. And then what do I multiply that by? The mass of the water, 0.819. It's going to be 0.0918 grams of hydrogen. But wait, there's more. Because now we know how much carbon and how much hydrogen are in the compound. Now we need to calculate the empirical formula. So if this is all the carbon and all of the hydrogen that were part of that, how do we calculate the empirical formula? Yep. Calculate the number of moles of each. 5. 0.09. So which one is smaller? The carbon. So we take our 0.9899, 0.09899, divide that by 0.036355. Divide this by the same. So that's 1, and then this is, it's 2.500. And so we multiply both by 2.
7.
2.7?
Yeah, 2.7. For the 36355.
I don't know what to tell you. Unless I type 5. I don't know. C2H5.
Look, I didn't do anything wrong on my calculator. So I was 2.7.
So how would you write it as the railroad track? Because I like the railroad track. 1.4366 grams of carbon. And then I rather that way I can have a clean.
Yeah, so you would do like the 0.0 or 0.4366 grams of carbon, and then this would be 12.01 grams of carbon, 1 mole of carbon. And it falls apart a little bit here because you're just picking then the result of that is the smaller, picking the smaller of those two and to do the next step. So whatever you get out of this, is this what you mean?
Yeah, I like the railroad.
Oh, okay.
So I'll do the second part and then I can pick over from finding out the smallest.
Yeah, so that would be this.
Yeah.
And then you would find some answer there and divide by the smaller of those to get to the final. Yeah, that railroad track method works a lot better for just straight unit conversions. When you start throwing formulas and stuff in, it does fall apart, but I also like that more. I think I'm in Chem 20 mode though, and I do this all the time. Okay. Well, shoot, still have some time, but not enough time for me to cover this whole problem. So this is the same thing, except now oxygen is part of the analysis. So in our previous problem, and I'll do this one later, record it and upload it. I know I'm a little behind on uploads right now, but I will upload that, those other videos, and I'll upload me working through that problem. So try working through that one on your own. The one caveat is that this had carbon and oxygen, did not have, or sorry, carbon and hydrogen did not have oxygen. So we can still do for this the exact same thing to figure out how much carbon, how much hydrogen. And once we know the mass of the carbon and the mass of the hydrogen, in this problem, we're also given the mass of the original sample. So this mass of 0.8009 grams is going to be equal to the grams of carbon plus the grams of hydrogen plus the grams of oxygen. So if you find grams of carbon, grams of hydrogen, you subtract those from your initial mass. Anything left over was oxygen. Does that make sense? Yeah, okay. All right, so now we're shifting into chemical reactions. So chemical reaction, right, one or more substance being converted into one or more different substances. This is another section we'll cover pretty quick because it is review for the most part. So like before, we were talking about combustion reactions. So that's when a substance combines with oxygen to form one or more oxygen-containing compounds. So if it's just carbon and hydrogen, or just carbon, hydrogen, and oxygen, your results are always going to be carbon dioxide and water. As soon as you start adding other things in, then you get other combustion products. We use combustion, arguably, for too many things. I don't even know if that's arguable anymore, but your car is a metal box powered by explosions. Those explosions are combustion. It's an internal combustion engine. So our chemical equations are shorthands for describing chemical reactions. We got reactants on the left, and products on the right. Reactants react, products are produced. Right, so one goes in, the other comes out. And in those chemical equations, we denote the state of that substance with a lowercase g, L, or S, right? Gas, liquid, or solid. And then aqueous, which, like everything in this class, is aqueous. If it's something that's dissolved in water, that's aqueous, and that's the lowercase aq. And equations provide a lot of, they're a shorthand, but they provide basically all of the useful information that you need to know about a chemical reaction. So the formulas and states of the reactants and products, relative numbers of reactants and product molecules, and then you can use that to determine masses of reactants used or products made or anything within that chemical reaction. So for example, combustion of methane. Methane gas burns to produce carbon dioxide and gaseous water, combustion reaction. If you look at the equation, remember how matter is neither created nor destroyed? This chemical equation, we have methane, CH3, we have oxygen, and then we have carbon dioxide and water produced, but we only have 2 oxygen atoms available in our reactants at the moment, and there are 3 oxygen atoms in the products. And so this is where we need to balance chemical equations. So for any chemical equation, the only way to balance it is to add prefixes or add coefficients to each of the chemical formulas. We can't change a chemical formula because the specific ratio, again, law of definite proportions, means that every molecule of water has to have 2 hydrogens and 1 oxygen. So since we can't just come in here and say, oh, we'll just make this a 3, that would be ozone instead of oxygen. We need to instead add or remove coefficients to get those to be balanced. Okay, so the other thing that's not balanced is hydrogen. So we only have 4 atoms of hydrogen, or we have 4 atoms of hydrogen in the reactants and only 2 atoms of hydrogen in the products. So, right, violates the conservation of mass, law of conservation of mass. So when we balance this by adding coefficients or changing coefficients, we would end up with 1 methane molecule, 2 oxygen molecules, 1 carbon dioxide, and then 2 water molecules. And then when you're counting these atoms, right, this 2 in front of oxygen means that there's 2 oxygen atoms. So that's 4 total, sorry, well, I guess they're oxygen molecules, 4 total oxygen atoms. So you multiply any element in the compound, for like water, you multiply the coefficient by its subscript. So if there's no subscript, that's 1. Okay, how many oxygen atoms are on the right-hand side of the following chemical equation? Yeah, so we got 2 times 3, that'd be 6. And then 4 times 2 would be 8, would be 14 oxygen atoms. How many are on the left? Yeah, should be if it's balanced. So 4 times 3 is going to be 12. Oh wait, did you said 14, but you thought I said?
You did the left side first.
Oh, yeah. Well, it should be the same on both sides. Yeah, so 14 oxygen atoms on both sides. All right, those are balanced. So there is, okay, I guess I'll say it like this. The balancing chemical equations is kind of like a Sudoku puzzle, but easier. Right? With the Sudoku puzzle, you don't have to solve it the same way. You're just trying to make 1 through 9 in every column, every row, and in every of the 9 larger squares. Same thing is happening here. Now, there are a lot of methods in something like Sudoku that make that easier to do. Similarly, for balancing chemical equations, there's some steps that you can follow to make your life a little easier. And those are these, right? So write a skeletal equation first by writing the formulas for the reactants and products. And again, we'll get more to nomenclature. That's more related to nomenclature. If you already have that, then you balance the atoms that occur in more complex substances first. And then always balance atoms in compounds before atoms in pure elements. The reason for that is, if you add a coefficient to a compound, you not only change 1 element, but you change 2 elements at least. And it's always easier to end on adding a coefficient for a single element if possible. A lot of the time, especially double displacement reactions, you won't be able to do that. But if you have the option, more complex substances first. Then balance atoms that occur as free elements last, again, because free elements are easier to balance by themselves. And then if the balanced chemical equation contains coefficient fractions, then clear them by multiplying the entire equation by the denominator of the fraction. The last step, of course, is to check. I'll kind of show you how I like to do this as well. Okay, so write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. So what's silicon dioxide? SiO2. I know we haven't covered nomenclature yet, but this will maybe impress upon you the necessity of it when we do get to it. So silicon dioxide, the di on the oxide means 2. So silicon 2 plus solid carbon, that's easy, C. And there will often be hints in questions like this that, right, to produce, so those were our reactants, these will be our products. So we can draw a reaction arrow in. We could even say,
Do you want us to do that like when we're writing stuff like this?
yeah. For Chem 1, you should be always writing those in. For Chem 20, not always, but solid silicon carbide. And what's carbon monoxide? CO, 1 oxygen. For silicon carbide, you would just need to know what it is, so because it's not an ionic compound. Okay. So, what is, looking at between the left and the right, reactants and products, what's not balanced? Oxygen. So the way that I often tackle these problems is in the situation where there's no, well, especially in situations where there's no individual free element, start with the thing that needs to be fixed. So we need to fix the oxygen. And so I'll look over to the right side and say, oh, I can add a coefficient of 2. So now we have the correct number of oxygens, but that changes the number of carbons. So how do I fix the number of carbons? Just a 2? Yeah, there's 3. So we could have also balanced the carbon first, but the carbon is a free element, and so we want to balance that last anyway. Is it balanced?
Yes.
Yeah. So we got silicon, we got one of those, silicon, one of those, oxygen, 2 of those, carbon is 3, carbon also is 3. Neato. Write a balanced equation for the combustion of gaseous ethane, which is a minority component in natural gas, in which it combines with gaseous oxygen to form carbon dioxide and water. All gaseous. So ethane, it's given there, C2H6, gas, combines with what? 2. Yeah. Oxygen's one of those special elements, diatomic. And then we've got carbon dioxide and water. So where should we start balancing this? Oxygen is off, but oxygen is also a free element. So we're going to do oxygen last. So, hydrogens, I hear hydrogens. All right, so how do we balance hydrogen? Right number of hydrogens. Now we got to balance carbon because we're waiting on oxygen. How many total oxygens do we have now? 7 oxygens. All right, how do we get 7 oxygens out of O2?
You don't.
You do, but only temporarily. Yeah. You don't, yes, but the way you do this is you say 7 over 2. All right, because 7 halves times 2 would give us 7.
You can do that.
Temporarily. We're not going to stay there. So now that just sets up the next step, which is to multiply the coefficients of all the compounds by 2. Because now if we double everything, we won't have that nasty fraction anymore. So I'm going to do it this way. Oh, well, I should do it like this. That's going to be 2. That'll be 7. This will be 4. This will be 6. So especially on combustion problems, you're very likely to see that kind of thing, where you need an odd number of oxygens. All right, one more. Oh, I forgot the G on water. So write a balanced chemical equation for the reaction between aqueous lead nitrate, aqueous potassium chloride to form solid lead chloride and aqueous potassium nitrate. So what's lead 2 nitrate? What's nitrate? NO3. What's the charge on nitrate? Yeah. So we need 2. It's lead 2. So 2 is the charge on the lead. Nitrate has a 1- charge, and that's aqueous. And then potassium chloride. KCl. Potassium has it's aqueous. Potassium has a 1+ charge. Chlorine has a 1-. And what's lead chloride? Lead 2 chloride going to be? PbCl2. And potassium nitrate, that's aqueous. Right, so the key when you have these polyatomic ions like nitrate, nitrate's a polyatomic ion, right? An ion made up of multiple atoms. Treat those polyatomic ions like their own separate entities. So unless it's a redox reaction, really, you're never going to be balancing the nitrogen separately from the oxygen. And the reason is that on the left side in our reactants, right, it's NO3, and on the products, it's NO3. So those are not separating from each other, so we might as well balance them as a single unit. And this is, what kind of reaction is this? It is a double displacement reaction, yeah. Okay, so what's not balanced? Nitrate, okay. How do I balance nitrate? 2 in front of potassium nitrate. So now on our reactant side, we only have 1 potassium, so we'll also put a 2 there. Yep, and that changes the potassium to 2, but it also changes the chlorine to 2. And if we look at our products, chlorine is 2, and we had 1 lead, and it balances. So double displacement reactions especially, you can just kind of pick one thing to start with and then fix that one. That'll change something else. Sometimes you have to fix whatever that is in the reactants, and then you keep bouncing back and forth until everything's balanced. There are situations, 2 possibilities that, well, okay. If you end up in a situation where you do this method where you start bouncing from one thing to another, and then you've gone through that loop a couple times, you probably wrote down one of the chemical formulas wrong. And it will keep going forever because there's no way to balance it. I believe there's also rare situations where you can do that, or things get confusing because you start with one element versus another. It's usually if an element exists in 2 things on the same side of the reaction. So like a combustion reaction where oxygen is part of carbon dioxide and water, if oxygen was also part of 2 compounds on this side, you might end up balancing and rebalancing and balancing and rebalancing in a loop. In that case, again, starting with the least complex thing, starting with also compounds that are not part of multiple compounds on one side of the reaction or the other. Essentially, recognize you're in a loop, start balancing from a different element next time. Just sort of reset and restart. Ready. We only went a little over.